You're all, I'm sure, familiar with acid-base indicators, which change colour depending on the pH of the solution. Well, there's another class of indicators called redox indicators. These change colour depending on whether or not they are in an oxidised or reduced state. One of the most well known is methylene blue. The oxidised form is, as the name would suggest, blue, while the reduced form, known as leucomethylene blue, is colourless. You can show this with an entertaining demonstration called the blue bottle. Glucose is dissolved in dilute sodium hydroxide in a bottle or flask with a lid, and a small amount of methylene blue is added. Once mixed, if you leave the bottle alone, it will soon go colourless. The alkaline glucose acts as a reducing agent and reduces the methylene blue to the colourless form. If you shake the bottle though, it goes blue again. Oxygen in the bottle's headspace, above the surface of the solution, dissolves in the solution and then reoxidizes the methylene blue back to its oxidized form. On standing again it goes clear, and you can keep on shaking it and letting it stand for a fair while as it switches between blue and colourless states. There are several other redox dyes that act in a similar way. Safranin, for instance, changes from pink to colourless and back. An interesting alternative is indigo carmine. This forms a basis of a demonstration known as traffic lights. The experiment is set up in exactly the same way, only using indigo carmine instead of the methylene blue. In this case, the dye has an intermediate partially reduced state as well. Once reduced, the solution is yellow. If you give it a gentle swirl, it oxidizes slightly and goes red, and then if you shake it properly, it oxidizes fully and goes green. On standing, it goes back through red to yellow, like a set of traffic lights, albeit one working out of sequence. So what's happening? In the first step, the glucose is converted to something called an acyloin, or alpha-hydroxyketone, an organic compound which has a hydroxy group next to a ketone group. The next step is a redox reaction of the acyloin with methylene blue in alkaline solution. The glucose is oxidized to diketone and methylene blue is reduced to colourless leucomethylene blue. If there is enough oxygen available, dissolved in the water, leucomethylene blue is immediately reoxidized to methylene blue, and the solution remains blue. However, when the solution is left to rest, the dissolved oxygen in the water is gradually consumed, and at the point where it has been completely used up, the glucose reduction of methylene blue proceeds with no opposing oxidation, and the colour of the solution rapidly disappears. When you shake the bottle, you add more oxygen to the solution, which then reoxidizes the leucomethylene blue back to its blue form. If you look at the structures here, you can see that the oxidized methylene blue has a significant stretch of alternate single-double bonds. This conjugated system is the chromophore that is responsible for the absorption of red and green light that gives the blue colour. You can see that the blue form does not have this lengthy run of single-double bonds, and so does not absorb light, at least not in the visible region of the spectrum, and so it is colourless. Without going into detail, the same principles hold for the reaction of safranin, indigo carmine, and all the other redox dyes which will work with this experiment.